Righto, Year 11, continuing with our work on sequences now, and just start with a little recap, I guess, before we head off into geometric territory. Let's just recap what we know so far about sequences. Hold on a second. Sorry, I just wasn't sure whether we were actually recording. Okay, so arithmetic sequences. Let's go through what the operation in an arithmetic sequence is from one term to the next. We can identify it through addition. So the operation is adding, and we're adding what we call adding a common difference. Adding a common difference, which we call D. All right, so that's the operation. Now the proof for an arithmetic sequence is that any term, so if we take, say, the second term and subtract the first term, we're going to get the same as taking the third term and subtracting the second term, and that is always going to give us D. So taking any term and subtracting the term in front will give us D. Now that's important. We'll do some examples today where you can see the application of that. Now the nth term, how do we find the nth term of an arithmetic? And it's good as I'm talking here and I'm throwing questions out there. You'll benefit much more from these if you answer the questions. I'm probably speaking slowly enough for you to be able to throw your answer in there or anticipate it before I've written it down, especially when we're doing things like this and we're just doing a little recap. So the nth term, if you know it, shout it out now, and then just happily confirm the result as I write it. So the nth term is the first term, and we just need n minus 1 by the common difference. Okay, and the sum of the first n terms, we had two. We had two ways of writing the same same expression, the sum to n terms. If we know what the last term is, occasionally we do, and with sigma notation we often do, it's first plus last by half the number of terms. Quite often though we don't know that last term, and it's going to be easier for us to use the other one, which says n over 2 twice the first term plus n minus 1d. Remember, that is achieved just by turning just by substituting un with u1 plus n minus 1d into this expression. We get the second one. Okay, so now into geometric. Now in geometric progressions, we don't add to get the next term, we multiply to get the next term. So we multiply not by a common difference, multiply in this case by a common. Now the difference is, so any term minus the term in front will give you the difference. In geometric, to define that common, it's division. It'll be any term divided by the term in front. So it's a common ratio, and we use the letter R to denote the common ratio. Okay, so the proof, as I've just hinted, is take any term and divide by the term in front, and that's going to give you our common ratio at whatever point in the sequence you take those terms. This is going to be useful in the work we do shortly. Now the nth term, this is new work now, so the nth term of a geometric sequence. So perhaps we'll just have a, okay, in a geometric sequence, we're going to get this sort of thing, aren't we? We're going to get 3, 6, 12, right? So I'm just started with a random number and I'm multiplying by 2. So in this case, my common ratio is 2, and just demonstrating what we were talking about before, if I take any term and divide by the term in front, I should get any other term divided by the term in front. So if you need to find what a common ratio is, then that's how you do it. Okay, so how do we develop the nth term? Okay, so if we start out generally, let's say we just talk about our first term is u1, that's going to be the first term. So let's just set up perhaps a little table. So u1 will be, right, if we look at it like this, and u2 u3. Okay, so my first term is always just u1, right? Our second term, right? So what happens to u1 in a geometric is that any term to the next term is multiplied by a common ratio. So u1 times r, we wouldn't write that as u1 times r, we just write that u1r. Okay, and then to get the next term, we would take our term 2 and we would take our term 2, which is u1 times r, and we'd multiply by r again. So we wouldn't write it like that. We would write u1 by r squared. So just u1r squared. This one here is u1r. Okay, so u4 is going to be u1r squared times r. So we're just going to multiply this here by r to get u4, which is u1r cubed. So if we extend this all the way out, if we dot 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 all the way out to the nth term, then what do we got? Well, we've got u1r to the something. Now let's have a little look at what this r to the something is going to be. So the fourth term had a power of 3 here for r. The third term had a power of 2. So our nth term is going to have a power of n minus 1. And that's a similar result, isn't it, to the arithmetic sequence. So here we are, we have our nth term of a geometric, which is just u1r to the n minus 1. So if we have a look at an example of that, so we might just say, all right, find the 8th term. So find the 8th term of this sequence. It goes 2, 6, 18. So we can identify our 2 as our u1. Our common ratio is 6 divided by 2, or 18 divided by 6. So that is 3. And I want to know, we want n equals 5, sorry, n equals 8, sorry, n equals 8. And we want to know what our nth term is. That's all the information. So let's get to work on it. The 8th term. So the 8th term is going to be equal to u1. All right, so let's start off with the formula. un is equal to u1 by r to the n minus 1. So u8 will equal u1, which is 2, times r, which is 3, to the n minus 1, which is 7. So 2 times 3 to the 7 into the calculator is 4374. So we can skip straight to the 8th term of this sequence using what we know about the development of a geometric sequence. Okay, so let's take a look at another example. Right, the number of terms in this sequence here. So again, let's take what we know. u1 is here. Now, what is r in this case? 0.45 divided by 0.15, or 45 divided by 15. So r is equal to, I'll just write down that, 45 divided by 15, which is 3. This is my nth term, un here. I don't know what n is. All right, that's find the number of terms. So that's what I'm trying to find. N. Okay, so if 36.45 is my un, I'm again using un equals u1 by r to the n minus 1. I know my un, I'm putting that in, that's 36.45. I know my u1, that's 0.15. I know my r, that's 3. I don't know what n is, so that's 3 to the n minus 1. So you get the idea with these questions is it's about taking the information, grabbing everything that you know, working out common ratios, common differences, first terms, all that sort of stuff. Starting with the formula. It's very much a formula-based area of work, this one. This is our little playground of formulas. Then we just are starting with that, plugging in what we know, and then just working out through algebra what it is we're needing to find. So in this case, 36.45 divided by 0.15. Just need to work out what that is. I've got my calculator right here. I'm just punching those numbers in, 0.15. So I get 243 here. So I can say that 3 to the n minus 1 is equal to 243. Now, I don't know what that is. I can use logs to solve this, but we haven't actually done logs yet. But I know that this has to be, n has to be an integer. So it's really just a matter of a bit of trial and error. It's the quickest way. I know that 3 cubed is 27, and 3 to the power of 4 is 81. And then if I multiply that by, again, to the power of 5, so 3, I get 243. So 3 to the power of 5 is 243. So therefore n minus 1 is equal to 5. And therefore n is equal to 6. So therefore there are 6 terms in this sequence. I'm going to do one more example. Okay, next example. Feel free to pause here, do the example yourself, and then come back and check on your answer with against what I get. So U1 here is 4. R is equal to negative 8 over 4, which is negative 2. And UN is equal to 2048. I need to know what n is. Righto. So 2048, which is my UN, is equal to U1 times R, which is negative 2. I need to bracket the negative 2 to the power of n minus 1. So 2048 divided by 4. Just put that through my calculator to get 512. So I now know that negative 2 to the power of n minus 1, negative 2 to the n minus 1 is equal to 512. So what power of 2, and let's think about this as a negative base. So I need a positive index in order for this to come out to be positive. So n has to be odd. So I could just trial and error with this. Maybe I can be a bit smarter about it. I know that, for instance, if I just drop the negative, I know that 2 to the power of, say, 6 is 64. And that's because I know that 2 cubed is equal to 8. And if I square both sides, I get that. 2 to the power of 6 equals 64. I obviously need to go a little further. If I multiply 64 by 4, I get 256. And 4 is 2 squared, so that means 8 is equal to 256, and then I just need to multiply by another 2. So 2 to the 9 looks like it's going to be equal to 512. So I therefore need 2 to the power of, so n must be equal to, so 2 to the power, is that right? Yeah, I thought I'd done something wrong here. I've left the negative off my equation down here. So dividing by, so it's negative 512, this looks better. So 2 to the power of 9 gives me 512. So negative 2 to the power of, I know that negative 2 to the power of 9 is going to give me negative 512. So therefore n minus 1 must equal 9. So therefore n is equal to 10. So how many terms in the sequence? Therefore there 10 terms. Okay, in exercise 1C, it might be a good idea to now to go and to do questions 1 to 3, which give you some practice on these type of questions that we've just looked at in those examples. I'll see you in a moment. Okay, next example. The fourth term of a geometric sequence is 54, and the sixth term is 486. So U4 is equal to 54. U6 is equal to 486, and we need to find out what R is. Okay, so we saw these type of questions in the arithmetic sequence questions. What we needed to do was set up two equations and solve simultaneously. We're going to do the same thing here. So from U4 equals 54, we can say, if we write this, U4 is equal to U1 by R cubed. And we're going to say, well, that's 54. That's what that information tells me. And this information here informs me that U1 by R to the power of 5. Remember that we're working with UN equals U1 by R to the n minus 1. So that is equal to 486. Okay, so if I label my equations, and now in order to solve simultaneously with my arithmetics, I typically had a subtraction to do, and that got rid of my U1. In this case, have a look at these two equations. How am I going to eliminate one of my U1 or R? Well, in this case, in this type of setup, we can divide equation 2 by equation 1, and what that will do is it will cancel our u1's out. We're just left with r. So our elimination for geometric sequence equations will be division. So I'm going to take equation 2 and divide by equation 1. Okay, so the result of that is going to be, I'm going to have u1 r to the power of 5 over u1 r to the power of 3, and that's going to be equal to 486 over 54. So dividing one equation by another is just the same in terms of validity as subtracting right through, or adding right through, which is adding two equations together, which is typically what we've done with linear style equations. Okay, so let's move this forward. My u1's now cancel, and I'm left with, on the left-hand side, therefore, r to the 5 over r cubed, which is r squared, and 486 over 54, I believe, is 9. So therefore, r is equal to plus or minus 3. Could it be either? Well, yes, it could. We can have either value of r is valid for this question. The common ratio could be 3 or it could be negative 3. Okay, you are now right to go with 1C, questions 4, 5, and 6. And I just have one more example, which will help you with questions 7 and 8. So see you in a moment. Okay, a final example before I set you free on questions 7 and 8 for this exercise. Reads as such: a minus 4, a plus 2, and 3a plus 1 are three consecutive terms of a geometric sequence. Find the two possible values of the common ratio. So I'll go back to how to prove that we've got a geometric sequence, and it is like so. So if I know that I've got three terms in geometric sequence, then I can say with utter confidence that a plus 2, any term over the term preceding it, will equal any other term. And in this case, I've only got three terms, so I've only got two possible ratios I can make. That must equal, they must equal to each other, and they must equal r. By definition, they're geometric, we're told that. Okay, so if this is the case, then I have an equation to work with, and I can go ahead and solve this for a. So off I go with that. I'll do a cross multiplication to get a squared plus 4a plus 4 equals 3a squared minus 11a minus 4. Okay, gathering all my terms, 2a squared minus 15a minus 8 equals 0. And by the way, pause this, go ahead and solve it. It's a great way of doing it, and then you get some instant feedback as to how you've gone with the question. You can always just pick it up at any point. Okay, I'm now going to factorize. I can see I've got a 2a and an a that are going to be my leading terms. Multiplying to negative 8, so I'm thinking minus 1, thinking a negative 8 in here will give me negative 16, and plus 1 in here gives me negative 15. I've got my product to minus 8, so that looks good. So I now got a equaling negative 1/2 or a equaling 8. Now, all right, so they're my possible values for a, but I'm after my values for r, the common ratio. So if I put those values in for a, I will get, right, so when a equals negative 1/2, I get negative 1/2 minus 4, which is minus 9 over 2, negative 1/2 plus 2, which is 3 over 2, negative 1/2 in here for 3a gives me minus 3 over 2 plus 1, which is minus 1 over 2. So that's my sequence when a is equal to negative 1/2. So what's my value of a? My value of r there? Well, I'll get it by taking 3 over 2 and dividing by negative 9 over 2. 3 over 2, rather than divide by negative 9 over 2, multiply by 2 over negative 9. Cancel, cancel, 1 there, 3 there. That looks like negative 1/3 to me. So my value of r when a is negative 1/2 is negative 1/3, and you can check with the next pair of fractions. Go back and solve for a equaling 8. Well, that gives me a sequence of 4, 10, and 25. What am I getting? What am I getting for r in this case? R is equal to 10 over 4, which equals 5 over 2. So my value of r is 5 over 2 when a is equal to 8, and the problem is solved. Okay, so you are now good to go with questions 7 and 8 of exercise 1C. See you soon.